Okay, so we are going to do an example of a position versus time determination graph, determination from a motion story. So going from a motion story to a position versus time graph. And the story that should be in the notes for this example problem says that Samuel starts at 3 meters from his house. The house will be the origin. And waits 2 minutes for his friend Peter. When Peter arrives, they walk 10 meters east to a park bench to have lunch. They walk at a steady rate. After about 1 minute, Peter realizes he left his water bottle where he was waiting and runs at a steady pace back to that location, where he instantly picks it up, turns around, and runs back at that same rate to the park bench. Okay, so how might this whole motion look in a position versus time graph? So we first want to define our axes. So remember, this horizontal axis, not the time axis, is time in seconds. And our vertical axis is position, and that has units of meters. Now the time axis starts at 0 when we start caring about the motion, so it's important for us to really remember how to define that. The initial motion that we're going to care about is when Peter starts to wait. And it's going to end when he hits the park bench to actually eat. So after he goes back and gets his water bottle, we're going to look at that whole motion. So here's the motion that's going to be represented in this time frame. Now we know that when the object is to the right of the origin, it is, or east, in this case it's an east-west. This is going to be east of the origin, it's positive. And this will be west of the origin, which is negative. His house is at the origin. Okay, we've defined that in the problem. All right. So where does Peter start? That's going to be the time equal to 0 at this crosshatch. It says Samuel. His friend's Peter. Where does Samuel start? Samuel starts 3 meters from his house. So let's say that 3 meters is right here, and I'm giving myself lots of room up there. It's 3 meters from his house, and it doesn't actually say whether that's 3 meters east or west. So let's say it's 3 meters, 3 meters east. So we're going to fix that in the notes. 3 meters east of his house. He waits for 2 minutes for his friend Peter. He's waiting. He's stationary. He's standing still. So there is our waiting time, our standing still. And we'll say that length is 2 minutes. Peter arrives and they walk 10 meters east to the park bench, where they're already at 3 meters from his house, and they're going to walk 10 meters further east. So they're going to end up even further from his house in the east direction. If he walks 10 meters, they're going to end up at 13 meters. So if this is 3 meters, he's going to end up here, let's say at 13 meters is up here. That's the 13 meter mark. Now it doesn't give us how much time. Well, this is just a conceptual graph of the story. So it says that they're walking at a steady pace. So steady pace, straight line. They're walking towards the east, positive slope. So we'll represent that steady pace like this. I've just picked a rate, all right? So you can say if this was 2 minutes, then it took maybe 4 minutes to get to the bench, to walk those 10 meters. They're walking pretty slow. All right, it then says after about a minute, so they're at the park bench, and they sit there for a minute. They're not moving. So if this was 2 minutes, it's about half that time. So they sit there, not moving. He realizes that he left his water bottle where he was waiting. Where was he waiting? At this location. He runs back to get it. Okay, now he's at 13 meters, going in the left direction. He's heading back west to where he was waiting. So he's moving leftward. So he should have a negative slope. And he's moving faster, so it should be steeper than this slope. It shouldn't take as long for him to get back to that location. These slopes have different steepnesses. Where he picks up the water bottle, turns around and runs back. So we're not having any transition changes, like he slows to a stop, picks it up, that sort of thing. Just does it instantaneously. And runs back at the same rate. So he's moving back to this 13-meter location, moving to the right, positive slope, but at the same rate that he traveled to get the water bottle, which is represented by the steepness. So even though he's moving now to the right, the steepness of that slope should look the same. I'm trying to represent it as the same. And once he hits that park bench, I don't care anymore. We're done. What happens after that? I don't care about it. It hits the park bench. So this represents that motion story. It's not very specific in some cases. We're getting general rates, but it does give you an idea of what Peter did. He hung out and waited. And I'm noticing that my story starts with Samuel and ends with Peter. So I will fix that in the notes. So Peter starts at a location waiting, not changing motion. Then, along with his friend, he moves at a steady rate to a new location, waits there. That location is further from his house. Then he realizes he needs to go back to the original location, so he moves in the opposite direction, represented by that negative slope. Goes very fast, so the steepness is different. Instantly grabs it, turns around, and these two steepnesses need to be the same if he's traveling the same rate. But one's positive because he's moving more east, and one's negative when he's moving to the left. Now nothing happens in this location, in this space on the graph. How come? Well, this is all stuff that's west of his house. He never goes there. This is position. And so since he never travels there, there's nothing in that graph. Had he gone past his house to grab his buddy Samuel or Michael, who lives west of his house, then we would have entered this world. But he doesn't. He stays always to the east of his house. So that's one example of a motion story that can be translated into a position versus time graph. Good job.